All right, so this is one of my theory talks for our tutorial today. We're working with elliptic curves where the coordinates are not real numbers. They are integers modulo a prime. And so the point of this mini lecture is to try to explain why that is allowed. So our formula for any elliptic curve is going to be y squared equals x cubed plus ax plus b. That's the Weierstrass form. And I'm claiming now that we are going to be working with these kinds of curves where our coordinates are going to be coming from the group z mod pz. So it's all right if that seems a bit strange. If you want to know where this curve lives, it's going to be a subset of z mod pz squared, the same way as graphs of ordinary real-valued functions exist as subsets of the Cartesian plane, or r squared, you might have seen it called. So this set here, the containing set, consists of all possible x and y pairs, where both x and y are integers mod p. And points that belong to the curve that I'm talking about are going to be those xy pairs whose coordinates satisfy the elliptic curve equation. So I would only be looking at x and y pairs, where x and y are both integers mod p, and they have to satisfy the equation y squared is congruent to x cubed plus ax plus b up to a multiple of p. So this entire thing is taken modulo p. So I'm working with a different group setting here. I need to be using that in my definition of the elliptic curve as well. So we can solve this kind of problem, or we can figure out whether or not an xy pair belongs to the curve, as long as my a and my b are also integers, right? The x and the y are my variables, and I'm saying now they belong to z mod pz. I want a and b to be integers as well, so everything makes sense, so that this multiplication makes sense and this addition makes sense. They all have to be in the same group for that algebra to work out. Just like we had a point at infinity for the continuous elliptic curves that I was talking about previously, we'll also have a point at infinity for my discrete elliptic curves. We'll still call it O, and that's still going to be the identity element. So that plays out the same way as it did for the real case. So just like before, this point at infinity is outside of the set z mod pz squared. It does not have coordinates belonging to z mod pz squared. It's an idealized point. You can think of this still as the point that lies on the end of a vertical line. Vertical in this case meaning that we will calculate a slope of a line. I'll do that in a couple slides from now. And if that slope is infinite, then this point at infinity is at the end of the it's at the end of the line which has infinite slope. Just like we saw with saying that we have a point at infinity at the end of a vertical line. So let me be a little bit more explicit in my example. I'm not going to graph any pictures today because I find that at this stage the pictures are not as helpful. They end up just looking like scatter plots. And you can still find some of the symmetries involved from having the y squared term. So we're still going to have that mirror symmetry, but it's less easy to identify that cubic shape going on in the graph. So for that reason, I'm not going to graph these things. We can still play around with coordinates. So we're going to need a prime number to set our coordinate system. I have chosen the prime 420,691. That is a prime number. So that will be my p, my lowercase p, for my coordinate system. And I've also picked a formula for an elliptic curve. And the points on the elliptic curve are going to be from the set z mod 420,691 squared. And the condition is that the y-coordinate squared should give me the same residue, mod my prime, as does the x-coordinate cubed plus 114 times x plus 100. Right? So that condition is what governs whether or not my coordinates are actually defining a point on this curve or off of this curve. So the philosophy involved is that we're still going to call this a curve because we're talking about solutions to a polynomial equation. We'll just use the word curve in a general sense, even though it'll just be discrete points. So off the bat, let's find some points that belong to this curve. I'll pick x-coordinate 0 to make this a little bit easier to work with. I know that 0 cubed is 0. I know that 114 times 0 is 0. I don't even need modular arithmetic for that. So my equation would then boil down to what are the solutions of y squared is congruent to 100 modulo a prime number. My prime number is big enough that 100 is its own residue. There's no modular reduction that we have to do. Since we're working modulo a prime, there's only ever two solutions to the square root problem. I know that 10 squared gives me 100, and I know that negative 10 squared also gives me 100. That means that I have two different coordinate pairs for points on this curve. 0, 10 is a point on this curve, and so is 0, negative 10. Or if you prefer, 0, 420, 681, right? Those would be the same coordinates because we're working mod a prime. Now both of these points have the same x-coordinate, and if we were going to graph them in the regular Cartesian plane, right, 0, 10 and 0, minus 10 are directly, vertically apart from each other. They have the same x-coordinate. A line plotted between them would be vertical. We can still use that logic in this setting. We can say because they have the same x-coordinate, a line drawn between them would be vertical. And that was our condition for finding the inverse of a point in the elliptic curve group. So because these two points have the same x-coordinate, the one of them plus the other of them makes the identity element. So we would get the point at infinity. So be careful that this addition right here is my group action, right? This is my group operation on elliptic curves where I have two different points. To add them together, I think about drawing a line and where they would meet. Because the line between these 2 points would be vertical, I get my identity element. That's how we defined this operation. Now, you'd be perfectly good to question whether or not that still works. We'll get to that on the next slide here. But for right now, let us find a second pair of points. We can do some more interesting things with them. So let me set x equals to 1. If x is equal to 1, I need to take 1 cubed plus 114 times 1 plus 100, and that'll be 225. And I have, again, made this nice and simple. 225 is 15 squared. And all of these are small enough compared to my modulus, 420,000 and change. So I don't need to worry about what the wraparound will do. I can just say that 1 comma 15 is an xy pair. These coordinates satisfy the elliptic curve equation. So this defines 1 point on the elliptic curve. And then 1 comma minus 15 will give me another point on the curve. So just like in the continuous case, we have this nice symmetry where every single point with x and y coordinates that satisfy the equation has its negative, right? The same x coordinate, but I'm going to negate the y coordinate. And again, these are done in my coordinates. So this is mod 42691. So just like on my previous slide, I could say that the point 115 and the point 1 minus 15 have to add up to make my identity elements. I add them together and I get my point at infinity. Let's do something a little bit more interesting. Let us add 115 and 0, 10. So I have two different points on the elliptic curve. I want to add them up together. My formula says we need to draw the line between them, find where it intersects the elliptic curve next, and then negate the y coordinate of the intersection point, right? That was what I said when we defined this group operation in terms of geometry. Now, I'm saying that graphing these things as a scatter plot, because we're only working with finitely many residues, is not really the most helpful way to go about it. So does the geometry idea still make sense? Well, I can still talk about lines and curves belonging to this coordinate space as being the solutions of certain equations. So I can still set up an equation that says y equals mx plus b, and I'll still call that a line. So just like in the ordinary, say Calc 1 sense, I want to find the equation for a line. Well, my slope is going to be the difference in y coordinates divided by the difference in x coordinates. So here, the line between my two different coordinates that I've got is going to have slope 5. And I can see already that if I've got slope 5, the equation for my line had better be y equals 5x plus 10, right? My y-intercept is just going to be 10 in this case. And I can still work with that equation and ask what coordinate pairs satisfy that equation. The set of those coordinates is what I'm going to be calling a line. The only thing we got to watch out for, because I am reducing mod a prime, is I got to make sure my denominator is not accidentally 0, right? So this would be a problem if I was working mod 7 and I got a denominator of 7. I cannot divide by that much in the integers mod 7. And this is also the reason why we don't use composite numbers. I'll talk about this in a bit more detail in the future. The problem is that with composite moduli, as we've seen in the past, some numbers you just cannot divide by. Whereas when you're working mod a prime, you can divide by whatever you like so long as it's not 0. And this will only be 0 if I have the same x coordinate in both places. And then I've got some number or some residue divided by 0, which I cannot do. So I would say that points like that would have an infinite slope, right? Now we're back to my earlier example. If this was 0, 10, and 0, minus 10, I would do my slope calculation. I'd get a 0 in the denominator. I'd say, oh, wait, no, that's an infinite slope. I don't want that. We can just figure this out and say that they add up to the point at infinity. So all of the formulas that I had in my previous lecture, where we calculate the slope m, and then we have a formula to give us the new x-coordinate, and we have a formula to give us the new y-coordinate, those still work, even though our coordinates are now integers mod a prime. So you can try this if you like, right? You can take this line, you say slope 5, intercept 10. What was the formula for the x-coordinate? What was the formula for the y-coordinate? Does that actually work? I'm not going to ask you to do those kinds of calculations by hand. So instead, we can have a computer do the work for us. Let's go to the calculator again. So my prime number was, again, 420, 691. My A was 114. My B was 100. My point P, I said, was 0, 10. My point Q was 1, 15. Can we calculate P plus Q? It gives me the result down here. P plus Q has x coordinate 24, y coordinate 420,561. So I'm not going to do that calculation by hand, and I certainly do not expect you to. So the purpose of this is just to help explain why this is a valid thing to work with. My next mini lecture will be talking about why we would want to do this, what makes discrete coordinates a practical thing and a desirable thing for elliptic curve cryptography. And I will see you in a bit for that.